Welcome to Lesson 8, Derivatives of Polynomials and Exponential Functions. So as promised, at the end of Lesson 7, I told you there are shortcuts. We do not have to always go through the limit process in order to find a derivative. So we're kind of switching gears with the beginning of Lesson 8, or with Lesson 8, and that now that we've really covered the idea and the concept behind limits and what a derivative really is and what it means and how to interpret it, we're going to kind of switch gears for a number of lessons. And we're going to just be working on how to actually find derivatives. So we'll start with lesson 8. There are some shortcuts here. This is a pretty straightforward lesson. And then we're going to keep going with derivatives of trig functions, and then some rules about products and quotients and all kinds of composite functions and things like that in upcoming lessons. So this lesson kind of represents the beginning of the shift in focus from concept to practical process. Okay, so let's go ahead and start with some derivative theorems. And so the first one is that the derivative of a constant function is 0. And so you could see that I've written it here. The derivative with respect to x of a constant is just 0. And we can actually prove this. One of the goals of this class is to introduce you to mathematical proof. And this is a pretty straightforward one. So what we're going to do is we're going to start by letting f of x equal c. So we're going to start with a constant function. And then we're just going to calculate f prime of x. So we know that's the limit as h approaches 0 of f of x plus h minus f of x all over h. But when I plug x plus h into this function, what do I get out? C. When I plug x into this function, what do I get out? C. So that numerator becomes c minus c, which is just 0. Now, I haven't actually plugged anything in yet. So I haven't plugged in an h equals 0, but I end up with a limit of a constant. And as we know, that would just be equal to 0. Okay. So it is different. This isn't a 0 over 0 scenario because c minus c is just 0. We're not plugging h into that. So we have 0 over something which is just 0. Okay. And then just to kind of further push the idea of what is happening conceptually here, if I were to graph an f of x function that's constant, so it's a horizontal line, what is the rate of change of the y values? How are the y values changing? Oh, they're not, right? So the rate of change of f, which is the y values, is 0 because they're not changing at all. So, I mean, you're effectively going to memorize that as a rule. Derivative of a constant is 0. But it's a pretty good idea to have to ground that in understanding. So then the power rule is the next one we're going to use. And what this rule tells us is if we're taking the derivative with respect to x of x to a power, and n can be any number, then what you're going to get is basically you're going to take that power and it's going to become the coefficient, and then you're going to subtract 1 on the power. So for example, if we were going to take the derivative with respect to x of just x, so that's like x to the first, the 1 would come down as a coefficient, and then we would subtract 1 on the power, which would give us x to the 0. X to the 0 is just 1, so the derivative of x is just 1. And if you think about it, y equals x is a line, and its slope is 1, right? So its rate of change is 1. All right, trying it on the next one, I'm going to take the derivative with respect to x of x to the 4th. So the power becomes the coefficient, and then the exponent in the derivative is going to be subtracted by 1. Okay. I think there's a couple more here. So pretty straightforward when it's written already with the as x to a power. Just apply the rule. You'll notice that in each one of the next examples, I don't have x to a power in the way it's first written. I have the square root of x. Can you write that as a power? You certainly can, right? So that would be the same as taking the derivative with respect to x of x to the 1/2. Then we can apply that power rule. So the original exponent becomes the coefficient, and then we subtract 1 on the exponent. Now it's really important for you to remember in terms of simplifying that your answers should not have negative exponents. So you will need to rewrite that. And you could leave it as x to the 1/2, or if you wanted to, you could rewrite it as the square root of x. It doesn't really matter to me, that you should not have a negative exponent in your final answer. Part of the reason for that is just in terms of simplifying. We are going to, once we figure out how to take all these derivatives, we're going to have to do things with them. And when we have negative exponents, it doesn't help us solve equations or even simplify them. So it's kind of just that first step for you to get in the habit of not leaving things in this form. Okay, carrying on to the next one. Again, 1 over x is not currently written as x to a power. In order to apply this power rule, it has to be x to a power. So you're going to want to rewrite that as x to the -1. Then you can apply your power rule. And again, just move that negative exponent down so it becomes a positive exponent. And last but not least, we've got kind of a combination here. We've got a cube root and a 4th power. So remember, you are able to write roots and powers. If I could do it correctly, it would be even better. So it's always power over root in terms of how you write that as an exponent. Power over root. And so then I'm going to take the derivative by putting the original exponent as the coefficient and subtracting 1 from the exponent. You can leave it like this, or you can rewrite that as a cube root. Okay, so the power rule, pretty helpful. The constant multiple rule basically just tells us that you can factor a constant out. If you're taking the derivative of a constant times a function, that's equal to the constant times the derivative of the function. So in essence, what it's saying here is you can pull a constant out before you take a derivative. And it will just remain, oops, I can't spell derivative either. Derivative. That was difficult. And the constant will just remain as a multiplier out front. So I got a couple of quick examples of that, kind of combining it with the power rule. So I have the derivative with respect to x of 3x to the 7th. So the 3 is the constant. So you can pull that 3 out front and then just multiply by the derivative of x to the 7th, which would be 7x to the 6th using the power rule. And then yes, you should definitely multiply together the 3 and the 7. So applying that same idea to the second one, we are probably going to need to rewrite this as pi times x to the -2 first. Then we'll pull that pi out front and multiply by the derivative of x to the -2. subtract 1 on the exponent, put the original exponent as a multiplier, and then I'm going to go ahead and just clean that up a little bit, move the negative exponent to the bottom, multiply the 2 and the pi, etc. Okay, so you can see we're just kind of building layers, little rule upon little rule that will allow us to just put together derivatives of some simple functions, polynomials for sure. All right, so our next rule says that if you're taking the derivative of a sum or of a difference, you can just take the derivative of each part and add them or subtract them together. This is kind of the last piece we need to be able to apply these rules to derivatives of polynomials. As you see in our first example here, we have the derivative of a sum. So we'll just do the derivative of this one plus the derivative of this one. And we have some constants that we'll pull out and then apply our power rule or our derivative of a constant rule. So I'm going to start by doing the derivative of this first term. We'll take the negative 16 out front, times that by the derivative of the t squared, which is 2t to the first. And then we'll add to that the derivative of the 485. What's the derivative of a constant? It's just 0. So that gives us negative 32t. Now, you may or may not remember this, but this was our position function for an example that we did in lesson 7. And we went through and we found the derivative of this using limits. And we did, in fact, get this answer. So now we can do it with the shortcuts, which is really helpful. But you don't want to abandon your limit process because you are going to be tested on it. Okay, so again, just kind of alternate notation, find y prime, which is just the derivative for this function. Why don't you go ahead and give that a quick try? Press pause. All right, and check it out. Pretty straightforward illustration of the examples that we've done so far, the rules we've done so far. Okay, so in number 3, it's actually asking us a question beyond just find the derivative of this. Okay, this is a question you're going to get a lot. You're going to see this question of find a horizontal, or when does something have a horizontal tangent line? That is going to come up over and over in these lessons that we're doing where we're learning about derivatives. And that's because those are actually going to be important points once we start using the derivative. So we're going to start using some questions to practice this process of figuring out what x values will this function have a horizontal tangent line. Okay, so what does that mean in terms of a derivative? If the tangent line is horizontal, what does that mean? What kind of slope does a horizontal line have? It has a slope that's equal to 0. Okay? So if the tangent line is horizontal, then that means the derivative is 0. So at any point when it's asking you, where is there a horizontal tangent line, you're going to find the derivative. You're going to set it equal to 0, and then you're going to solve. So this process is going to not change. Your derivatives and how you find them might, evolve from lesson to lesson. But anytime you're asked, where does it have a horizontal tangent line, you're going to go through that process. So in this case, you're going to take a derivative. Which should give us 3x squared minus 3 in this case. You're going to set it equal to 0, and then you're going to solve. We'll go ahead and just factor here. And so you can see that you have 2 values where x is plus and minus 1. It did ask us for points, so we could plug those 2 points into the original function to get the y values. So these would be the 2 points where that function has a horizontal tangent line. Okay, and then for 4 and 5, if we look at these two problems, we see that in the first one, I have a product of two functions, and in the second one, I have a quotient. And you'll notice that we did not have any rules in this lesson about derivatives of products or derivatives of quotients. It didn't say, oh, you just multiply the derivative of one times the other, because you don't. Okay, so you have to be careful here on both of these problems. Okay, you do not have a rule that tells you what you can do with products and quotients. So what you need to do is use some algebra simplification to get these things as x to a power for each term. Okay, so you're going to have to use algebra to rewrite as terms with powers of x, because that's the rule we have. It's a power rule, not a quotient or a product rule. We do have those coming up, but they're not as straightforward as just multiply the quotients together or divide them. So what I mean for this would be, if I take this first function, I'm going to rewrite the square root of x as x to the 1/2, and then I'm going to distribute that so that I have x to the 3/2 minus x to the 1/2. Now I have a function where I can go ahead and apply the rules that we do have. Which in this case would be the power rule and the difference rule. And, at this point, you can rewrite it as a square root of x if you want to, but you definitely do need to get rid of that negative exponent in the second term. Okay. So if that's the process we need to follow, we need everything written as powers of x. How do we do that same idea, that same process for number 5? Now I have a quotient. Since this is a monomial, it can just divide into every single one of the terms above. So basically, f of x will equal this. And then, of course, I can simplify. So x squared plus 4. And then I guess I'll write that as 3x to the -1, because now I have it in a form that I could use the power rule. So I can take the derivative term by term. The derivative of 4 would just be 0. And clean it up by getting rid of that negative exponent. So it's really important with rules 4 and 5 that you make sure that you are not making up a rule that doesn't exist, right? Now, I'll also mention one more thing about those. We are going to learn product and quotient rules in a subsequent lesson, possibly even the next lesson. But sometimes it's actually easier to do it the way that I just did here, which is the little bit of algebra manipulation first, and then just take the derivative term by term. A little bit of algebra manipulation, term by term. The quotient rule in particular is kind of complicated, and to do it for something this simple ends up being more work. So I'm going to address that a little bit more in lesson 10's videos, but I just want you to always be thinking about, am I doing this in the most efficient way? Okay, and for our last example in this set here, this should be really straightforward. I'm going to have you try this as well. So press pause and give it a try. What has happened? I've given you a position function, and I'm asking you to find the acceleration at t equals 2. So remember, what's the derivative of position? Velocity. And what's the derivative of velocity? acceleration. So you're going to need two derivatives and then plug in 2. Give it a try. Okay, take a look, compare your answers with mine. Should be pretty straightforward, just taking a couple derivatives and plugging in 2. Okay, we do have one more rule in this lesson, and that is the derivative of the natural exponential function, which is e to the x. The derivative of e to the x is e to the x. It's its own derivative. That makes it easy to remember. So we can just throw that in now into these examples if we're trying to find a derivative and it involves an e to the x. Well, that will just stay e to the x. Oh, I probably should have rewritten this as 6x to the power over root. So then that makes it a little bit easier for me when I go to apply my power rule. Always simplify. So that would be a 4 over x to the 1/3, or 4 over a cube root of x. All right, and then our last example has a similar question. We dealt in earlier with a horizontal tangent line, and that meant the slope was 0, so the derivative was 0. This time we're asking about a tangent line that's parallel to this line. So parallel lines have what kind of slopes? And what's the slope of this line? So I want a tangent line that has a slope of 2, which means I'm going to take the derivative and I'm going to set it equal to 2. So y prime, oh, it's just e to the x. So the derivative is just e to the x. Well, that's pretty straightforward. When does that equal 2? Well, I'm going to need to ln both sides. The ln and the e will cancel. So it will happen at x equals ln 2. If that is my x value and I plug that into the y, well, the e and the ln cancel again, and I'm left with just 2. Okay, so just to recap a couple of tips here about starting to use these rules. Radicals, you definitely are going to need to radicals and quotients. If there's an x in the denominator, you're going to need to rewrite those into exponents, so you can use the power rule. Distribute things so you can convert each term to exponents. If the denominator is only one term, it can be divided into each numerator term separately. So these two are what we just did in numbers 4 and 5. The tangent line is horizontal when the derivative is equal to 0. Parallel lines have the same slope. And in case you get a question that's asking you about it, perpendicular lines have opposite reciprocals. So you need to flip it and change the sign. Just reminding you in case you forgot.